Welcome to The Explainer. Today, we're diving deep, way down into the guts of our digital devices. We're going to peel back all the layers to see how they actually store every single piece of information, from the photos you take to the messages you send. So let's get into it.
All right, let's kick things off with a simple question. When you send an emoji, say this little bear here, what is your phone actually storing? What is it sending over the network? Because I can promise you, it is definitely not a tiny picture of a bear. Nope. To your computer, that friendly bear emoji looks like this. A long and, let's be honest, pretty intimidating string of zeros and ones. This right here is binary, the fundamental language of every single digital device on the entire planet. So if we want to understand how our devices really work, we have to start right here with this foundational language. It all boils down to just zeros and ones. Everything is built from just two super simple concepts. First, you have the bit. It's the smallest possible piece of information you can have. Think of it like a light switch that's either off, a 0, or on, a 1. Then you just group 8 of those bits together and you get a byte. And with those 8 bits, you can suddenly create 256 unique combinations. Now, computers, they are perfectly happy crunching billions of these bits every second. But if you're a human analyst trying to make sense of a file, well, trying to read a screen full of this would be an absolute nightmare.
Which, of course, perfectly illustrates why we needed a better way. There just had to be a more human-friendly system to bridge that gap between our brains and the machine's language. And that solution is called hexadecimal. Just think of it as a convenient shorthand for all that messy binary. It uses 16 symbols, our usual numbers 0 through 9, plus the letters A through F. And here's the magic. A full byte, all 8 of those bits, can be perfectly squished down and represented by just 2 of these hexadecimal characters.
And check out how simple the conversion is. You take one byte, like 11010101, you just split it right down the middle into 2 4-bit chunks. Each of those chunks then translates directly to a single hex character. So 1101 becomes D, and 0101 becomes 5. All of a sudden, that long binary string is just D5. Way easier to read, right?
But wait, there's another little wrinkle here. Hexadecimal makes it easy to read a single byte. But what about bigger numbers that take up multiple bytes? We need to know which order to read them in. And this concept, this is called endianness.
See, different computer systems handle this differently. A big endian system stores the most significant part first. It's kind of how we read numbers. It feels natural. But a little endian system flips it, storing the least significant part first. Both are totally valid, but you absolutely have to know which system you're dealing with, or the data will be completely scrambled.
Okay, so we've got a way to store and read numbers. Now let's build on that. Let's see how this foundation lets us represent all the text, characters, and emojis that we use every single day. This journey started way back in the 60s with ASCII, which was great if you only spoke English. Then came other standards that tried to add support for more languages, but it created absolute chaos. Imagine sending an email where all the accented characters just turn into total garbage. It was a mess. And this is exactly why we so desperately needed something better. And finally, we got it. UTF-8, a universal standard that can represent basically any character or symbol you can think of.
And this, right here, shows the real genius of UTF-8. Look at the letter B. It's a common English character, so it only needs 1 byte. Super efficient. But the German character A needs 2 bytes. And our friend, the bear emoji, well, that needs a full 4 bytes to represent it. It's this variable length system that makes it both powerful and incredibly efficient.
So we've got numbers, we've got text. The next crucial piece of this whole puzzle is how computers handle time. Here's the thing, computers don't really get months, days, or hours. Instead, they just count. They store time as one single massive number. It represents the number of seconds that have passed since a fixed starting point, and we call that the epoch. And to make sure there's no confusion with time zones, they always count in UTC, or Coordinated Universal Time. And here's a super important detail, especially if you're in digital forensics. Not everyone uses the same starting line. Android systems use the classic Unix epoch of January 1st, 1970. But Apple devices, they start their clock way later, on January 1st, 2001. So a timestamp of 0 means two completely different things depending on the device. This whole system of counting seconds leads to a famous issue, kind of like a Y2K bug for a new generation. See, older systems used a 32-bit number, which can only count up to about 2.1 billion. Well, in the year 2038, we're going to hit that many seconds past 1970. The counter will then wrap around to a huge negative number, sending the date back to 1901. Thankfully, most modern systems have already switched to 64-bit numbers, which won't run out for about 292 billion years. So we've dodged that bullet. Mostly.
So you might be wondering, if a timestamp is just a number, couldn't a smart criminal just change the clock on their device to cover their tracks and maybe create a false alibi? Well, it's not quite that easy. The key thing to remember is that log files and databases are written sequentially. So take a look at this table. Each entry has an ID that just goes up by 1, 345, 346. But wait, look at ID 347. The timestamp suddenly jumps backwards in time before correcting itself on the very next entry. That sticks out like a sore thumb. It's a massive red flag that the device's clock has been tampered with. Okay, so let's bring it all home. We've gone through binary, hexadecimal, how text is stored, and timestamps. Why does any of this fundamental, low-level stuff actually matter in the real world?
Because these are the absolute building blocks of our digital lives. Every single thing on your device, from a silly emoji to a critical piece of evidence in a case, is just a collection of zeros and ones. Hexadecimal is our decoder ring. UTF-8 is our universal translator, and timestamps are our digital calendar. Understanding these fundamentals is how you unlock the secrets hidden deep inside all that digital data. So I'll leave you with this final thought. Knowing now that every text you send, every photo you take, every single tap on your screen leaves a permanent record written in this secret language of bits, bytes, and timestamps, what story is your data telling about you?